Hi dear students, hearty welcome to our YouTube channel Anveshika Andhra Pradesh. Today I am going to explain about simple harmonic motion.
Dear students, before going to learn about simple harmonic oscillator, let us know what is motion, what are different kinds of motions, and especially we have to know about simple harmonic motion. So for motion, if the position of the body changes from time to time, then the body is said to be in motion. Suppose the position of the body doesn't change with respect to time, then it is said to be in rest. Now, to know the different kinds of motions, firstly, what is translatory motion? If a particle moves from one point to another point, that is from point A to point B, say let us consider this is point A and another point, say this is B, and if the particle moves from A to B like this, then this motion is called translatory motion. Observe here, one bike, one bicycle and a car are moving from one place to another place. This motion is called translatory motion, and if the motion of all these vehicles are in straight line path, then the motion is called linear motion. Now, what is circular motion? Let us see here, if the body from a fixed distance and from a fixed point moves around that fixed point, then this motion is called as circular motion. The example for this is giant wheel motion. So the motion of giant wheel is circular motion, and now if we see the motion of a tip of the seconds needle of the clock around the fixed point, or the tip of the minute's hand or tip of the hour's hand, will be in circular motion. Now let us know another type of motion, that is periodic motion. If the motion of a body is repeated itself at regular intervals of time, then its motion is called periodic motion. An example for this is revolution of earth around the sun. Here observe the motion of the earth. Here it is winter season, it is spring, it is now summer, autumn and again winter. So in this way the motion of earth around the sun is repeated itself at a regular intervals of time. So the motion of earth around the sun is example for periodic motion. Another example for this periodic motion is motion of a needle in a sewing machine. Observe here, here also the motion of the needle repeated itself in a regular intervals of time. So the motion of needle in a sewing machine is also an example for periodic motion.
Coming to next type of motion, that is simple harmonic oscillations. So when we talk of oscillations, what do we have in our mind? Some object which is going from one place to another place and coming back to the same place and then repeating its path. That what we call oscillations. Pendulum is the simple example for this. And I have this pendulum, this is string and this is bob. Now the position of this pendulum, that is the quantity which will change its value. Suppose the position of this pendulum is here, and when it oscillates, it goes here another position, it goes here another position, it goes here another position, and it goes up to some extreme position, and then it retraces those positions and coming back to the first extreme position. So that is how it oscillates. we can say that it oscillates. Observe here, it goes from one position to another position and retraces those positions, and then the whole thing repeats. So that is what we call oscillations. We have many oscillating systems that we encounter in our life. Here I have 2, 3, 4 things. Let me show them one by one. I have this iron scale oscillating system. One end of this scale is fixed and the other end is free to move. When I push it and releases, you have to observe how it oscillates. Now I am placing this system very close to you. Please observe. Here is the position. When I am pushing and releasing, observe how it is oscillating. It goes from one position to the other position and retraces those positions, and then the whole thing repeats. So we have oscillations. See, this is another example for oscillatory motion. This is a toy. Here head is one system and hand fan is another system. If you observe the head of the toy, it oscillates in an up and down motion periodically. Similarly, if you observe the hand fan, it oscillates to and fro motion periodically. This is another toy. Here, hand of the toy is oscillating system. It is also oscillating in to and fro motion periodically. So, we have oscillations. I have this glass, another example for oscillating system, and if I placed here on the table like this and I displaced slightly from here, observe how it changes. See here, it goes this side and this side and also that side and also this side. So it is oscillating. The position or the angular position is changing with respect to time from one extreme to the other extreme. So we have oscillations. Another example, I have this beaker with water and I have this small vessel. If I put this in this water, see what happens. It floats. And if I press it down, it oscillates. Here we can note two kinds of oscillations, up and down and angular oscillations. See the motion of this pendulum. It is a circular motion, and if we observe the projection of this motion on the mirror, see it is straight line path or linear motion. See here, now it is in equilibrium position, that is stable equilibrium position. If I pull it and release, it oscillates around that mean position where the potential energy is minimum. So it is an essential condition somewhere the potential energy is minimum so that it oscillates around that mean position. So assume that this is the mean position and the oscillations, to and fro oscillations of pendulum is around that mean position. At any instant of time, if the position of this pendulum bob is here, then the length from this mean position to this position is called displacement, and if it is here, this is another displacement, and if it is here, this is another displacement. And suppose if the pendulum bob is at extreme position, then the length from this mean position to this extreme position is called maximum displacement. So that maximum displacement from its mean position, also called as amplitude. If I release this pendulum bob from this extreme position, it is moving in this direction and crosses this mean position and reaches the another extreme position. So after that it has to move in the same direction, or it has to move away from this mean position. Is it happening like that? No, it is not happening. And another thing, at extreme position, the velocity of this bob or the any particle at extreme position, its velocity is 0. So it has to stop there. Is it happening like that? No, it is also not happening. It is coming back. So some force is acting on this particle, which is called as restoring force. So due to that restoring force, it is coming back and crossing the mean position, and it oscillates to and fro motion, and this motion is repeating itself in a equal intervals of time. So see here, I am leaving. This is oscillations. See these oscillations. Here the displacement of this pendulum bob is very less, hence the restoring force is also less. If the displacement of this pendulum bob is more, then automatically its restoring force is also more. So in this way, the restoring force is always directly proportional to the displacement of this pendulum bob from its mean position. Also observe here, the displacement of this pendulum bob from its mean position is this one, and it is acting in this direction. But here the restoring force is opposite to this displacement, and it is acting towards the mean position. And coming to this side, here is the displacement of this pendulum bob, and it is in this direction. And here also the restoring force acting opposite to the displacement, and it always acts towards the mean position. So in this way, if we observe whole thing, the restoring force is always directly proportional to its displacement and is in opposite direction to the displacement, and also it always acts towards the mean position. So when a body repeats his motion again and again from its mean position in a definite interval of time, then that motion is called periodic motion. And if the path of that body is in straight line, then that periodic motion is called simple harmonic motion. Again observe here, the displacement of this pendulum bob is very less, and clearly watch this one, the path of this pendulum bob is straight line path, that is linear motion. So if we completely observe this one, the position of this pendulum bob is in this position, and also this position, and also this position. So it is continuously repeating its position again and again from its mean position. So it is a periodic motion, and since it is less displacement, so it is a linear motion. And also here the restoring force is directly proportional to displacement of this pendulum bob, and is also in opposite direction to that displacement, and it is also acting towards the mean position. So this pendulum executes simple harmonic motion. Another example for oscillatory motion is mass loaded vertical spring. So here I have put this spring, and through this spring I have suspended this mass, and if I pull it down, it goes up, and if I push it up, it goes down. So in this way it is oscillating. So here the position of this mass will change periodically from one extreme position to the other extreme position. So we have oscillations. Assume that the position of this scale is mean position of this mass, and if I pull it down it goes up, and if I push it up it goes down. So this is up and down motion around this mean position. So here also some force is acting on this mass to bring back its position. That force is known as restoring force. And this restoring force is directly proportional to the displacement of this mass from its mean position, and it is in opposite direction. Also, this restoring force acts towards the main position. Also, it is a periodic motion. Why? Because the up and down motion is repeating itself again and again from its mean position in a definite interval of time. So, this is a periodic motion. And also, it is linear motion. See clearly, it is a linear motion. So, the mass loaded spring is periodic motion and it is linear motion, and also the restoring force is directly proportional to the displacement of this mass from its mean position, and it is in opposite direction to the displacement direction, and also it is acting towards the mean position. So the mass loaded spring is executing simple harmonic motion. These are certain references with the help of which I have prepared this presentation. You can also use these following books for your reference. The images and the video clips which I have used here, the credit completely goes to original owners. So dear students, in today's class we did so many experiments to understand about different kinds of motions and especially about simple harmonic motion. In the next class, we will derive the differential equation of simple harmonic motion and its solution. Until then, be well, do well, and read well.